Imagine the possibility of sending metal sheets soaring into the upper reaches of our atmosphere through a method many have overlooked, the phenomenon known as photophoresis. This remarkable effect, which allows for slight lifting forces without the need for any moving components, presents a fascinating concept that could revolutionize how we explore the sky. Most individuals would likely recognize the apparatus showcased in the accompanying image. Yet not everyone is familiar with its actual name, the Crookes radiometer. As indicated by its title, this device demonstrates a notable reaction to light exposure, namely the spinning motion of its blades, which can be witnessed in action here. https://v6y5hmfa. There's a common misconception regarding the underlying physics at play, and this is where things get intriguing. The forces that cause the blades to rotate are part of the photophoresis phenomenon, which can exert influence on various structures when positioned in an atmosphere with significantly low density. A recent study conducted by a team of researchers has brought to light the potential of utilizing photophoresis to elevate thin metal sheets into the upper layers of Earth's atmosphere, as well as the skies of other planets. Their goal is to create devices that can reach atmospheric levels that are too high for balloons, yet remain below the operational altitudes of satellites. Initial prototypes have even been tested closer to Earth's surface, paving the way for future explorations. Understanding photophoresis. It's astonishing how often the Crookes radiometer is misrepresented, often linked incorrectly to concepts of radiation pressure. The prevalent belief is that the blade's darker sides collect more photons, which each carry a minute quantity of momentum, thus pushing the darker side consistently. However, this explanation has a fundamental flaw. When considering the photons that bounce off the shiny side, they actually impart even greater momentum. If the blades were truly spinning due to radiation pressure, they would rotate in the opposite direction than what is observed. The essence of photophoresis lies in the temperature gradient that emerges between the dark, heat-absorbing side and the cooler, reflective side of the blade. As gas molecules come in contact with the warmer, dark surface, they gain thermal energy, causing them to dart away faster than their initial speed. Under normal atmospheric conditions, these gas molecules do not travel very far due to frequent collisions with other molecules, preventing substantial differences from forming. However, the Crookes radiometer operates within a sealed glass dome that maintains low air pressure, allowing gas molecules to travel farther away from the dark surface before encountering other molecules. This creates a region of lower pressure at the dark side of the blade, prompting gas to rush in from the shiny side to fill this gap, resulting in the initial push that sets the blades into motion. Despite its ability to demonstrate this effect, the Crookes radiometer is not very efficient. This inefficiency has led scientists to seek alternative designs that could enhance the force generated. One promising approach involves using two thin metal sheets, one painted dark, the other light, positioned parallel to each other. These sheets would be extensively perforated to reduce their weight, and a portion of the holes would be connected via short pipes, resulting in a structure playfully dubbed nano-cardboard. These pipes serve multiple functions. They connect the two sheets, act as insulators to retain heat between the dark and light sheets, and provide a direct pathway for air to move from the top of the light-colored sheet to the bottom of the dark one, thereby offering an element of directed thrust that aids in maintaining the sheets aloft. Investigating optimization. There are numerous variables to consider in this optimization process. Parameters such as the distance between the sheets, the density of the perforations, and the quantity of these holes that have connecting pipes can all be adjusted. For this purpose, researchers devised a modeling system aimed at exploring various configurations to maximize lift. The reasons driving this research will be explored shortly. The researchers outlined their methods, stating, "The inputs to the model are the geometric, optical, and thermal properties of the disk, ambient gas conditions, and external radiative heat fluxes on the disk. The outputs are the conductive heat fluxes on the two membranes, the membrane temperatures, and the net photophoretic lofting force on the structure. Typically, to achieve any lift, the gas conditions have to resemble those found inside a Crookes radiometer, where pressure levels are much lower than what we experience at sea level." From their modeling, several trends emerged that should inform any designs moving forward. First, the density of perforations must strike a balance. In denser atmospheres at lower altitudes, numerous perforations can increase stress on larger sheets, while benefiting smaller items in higher altitudes. Furthermore, contrary to what one might expect, lift does not scale up with surface area. In fact, it typically decreases as larger sheets manage to equilibrate more readily with surrounding temperatures. Remarkably, a square millimeter of this nano cardboard can produce over 10 times the lifting force per surface area compared to a 10 centimeter square of the same material. Interestingly, the modeling predicts that the maximum lift occurs within the mesosphere, located just above the stratosphere at altitudes between 50 to 100 kilometers above Earth's surface. The power of light and liftoff. In their quest, the research team constructed several nano cardboard sheets to validate their model's predictions. These lightweight sheets, primarily composed of chromium, aluminum, and aluminum oxide, weighed an impressive 1 gram per square meter. Upon exposure to a laser or white light emitting diode, they generated a palpable force on testing apparatus. Granted, the atmospheric conditions were sufficiently sparse. Under sunlight equivalent exposure, these devices even produced more force than their own weight. This fascinating outcome illustrates the remarkable potential of harnessing a relatively obscure and subtle physical effect to create devices capable of levitation in the upper atmosphere, all powered simply by sunlight. A truly exciting prospect. However, the researchers harbor ambitions that extend beyond mere demonstration. The mesosphere presents a unique challenge to study. The sparsity of gas rules out conventional balloons and aircraft, yet it remains too dense for satellites. Thus, the research team's ultimate vision involves transforming one of these devices into a craft equipped for carrying scientific instruments. Achieving this vision, however, introduces complications. Surgical structural enhancements for instrument support must be added, alongside the instruments themselves. Even in the area of the mesosphere, where lift is most effective, these devices generate limited lifting capacity. Moreover, there is the logistical challenge of elevating these devices, as they won't produce enough lift within lower atmospheric layers. They would need to be transported into the upper stratosphere with some form of carrier, then released delicately to avoid damaging their fragile composition. Furthermore, unless they are launched during the polar summer, they will most certainly descend back down at night. While this vision may not be an insurmountable one, it certainly faces numerous substantial obstacles before any practical application can be realized on Earth. And that's not even considering the potential for similar explorations on Mars, where one could also utilize this system to study the mesosphere. Even if the original ambitions don't manifest as anticipated, the underlying physics remains an enthralling subject that brings to light the complexities of our world. What are your thoughts on the potential of using photophoresis for exploration? Do you believe the obstacles are too great, or could this simply be a stepping stone to greater discoveries in atmospheric science? Share your insights in the comments.